Since we're on the topic of gas mixtures, let's just answer the gas mixture problem from chapter 15 now. A mixture of helium and argon occupies 1 times 10 squared liters, 100 liters. So we have a 100-liter container of helium and argon. The partial pressure of helium is 0.6 atmospheres. And so the pressure of helium inside here is 0.6 atmospheres. And the partial pressure of argon here is 0.4 atmospheres. What are the partial volumes of the two gases? What is it? 100 liters? Yeah. That's right. So if the helium is 0.6 atmospheres, and 60% of the collisions are from helium, and the volume of helium is 100 liters. What is the volume of argon? 100 liters. Both. So we have 100 liters of helium, we have 100 liters of argon. That's what we have. And so, but their answer is each gas fills the volume of the container 100 liters. So that means we have 100 liters of helium and we have 100 liters of argon. A gas, either pure or mixture, is made up of tiny particles that are widely separated. All right. So, the second part of the answer is not relevant. A mixture of argon and carbon dioxide gases is maintained in an 8.05 liter flask at a temperature of 43 degrees C. So let's take a look at this next mixture. This is going to be argon and CO2. Argon and CO2. We're going to have 8.05 liters. Temperature is 43 degrees C. So the pressure of argon is 0.326 atmospheres. The pressure of CO2 is 0.234 atmospheres. What is the total pressure?
0.56 atmospheres.
Yeah, 0.56 atmospheres. So P total is going to be the sum. It's going to be the pressure of the argon plus the pressure of CO2, which is going to give us 0.560 atmospheres. That's it. 1 and 2 are examples of Dalton's. This is called Dalton's law. 3. Is also Dalton's law. Atmospheric pressure is a total pressure of a gaseous mixture called air. Atmospheric pressure is 749 torr on a day that the partial pressures of nitrogen, oxygen, and argon are 585 torr, 144 torr, and 19 torr respectively. What is the partial pressure of all the other gases in air? Well, there's some minor components in air, like helium, etc., CO2. And so P of air is equal to 749 torr. And that's going to equal the pressure of the nitrogen plus the pressure of the oxygen plus the pressure of the argon plus the pressure of the other gases. So if we want the pressure of the other gases, then that's going to be P of the air minus these nitrogen, oxygen, argon. I'm going to write it in here. Nitrogen minus the pressure of oxygen minus the pressure of argon. And so we get to just subtract those. So the pressure of the other gases is equal to the total minus the nitrogen, oxygen, argon. That gives us 2 torr worth of other gases that are present. Again, another Dalton's mixture. The stopcock connecting a 1.00 liter bulb containing oxygen gas at a pressure of 540 torr and a 1.00 liter bulb containing helium gas at 776 torr is opened. And so let's say I have 1 liter of oxygen, O2 gas. Pressure is 540 torr. And this is connected to another box. There's a valve here. And this is going to be 1.00 liters. Helium gas at 776 torr. So if I open this valve, what's going to happen? Well, if I open the valve, then the 2 gases can mix. They're no longer separate. So this is a combination of problems. If I open the valve, then the volume changes. Originally, with the valve closed, the green gas is confined to 1 liter, but if I open this valve, then the green gas can spread out over 2 liters. The same thing with the red gas, it can spread out over 2 liters. So essentially the volume is doubled. If I double the volume, that's going to change the pressure. And so I'm going to get the new pressure of oxygen. The final pressure of oxygen is equal to the initial volume over the final volume times the initial pressure of oxygen. And so the initial volume of oxygen was 1.00 liters. The final volume is going to be 2.00 liters because now the oxygen is free to go over both containers. And that's going to be 540 torr. Was the original pressure, and so the pressure is going to be cut in half, so it's going to be 270 torr. And then I do the same thing for the pressure for helium. It's going to be V initial for helium over V final for helium times P initial for helium. So V initial is 1.00 liters if it's the same as oxygen. The final volume is the same, 2.00 liters. Comes the initial pressure of 776 torr. So I have that 350. 363 torr. And so I have 270 torr of oxygen after opening and 363 torr of helium. And if we combine those, I'm going to get a total pressure of 603 torr of total pressure.
It was 388 torr of helium.
388?
Yeah.
Okay. 388 for which one?
Helium.
Helium, this one?
Yeah.
388, thanks. 388, screwed that one up. So this is going to change this to what? 558? Is that right? 658. 658. Okay. So that would be another Dalton's, but this one required an additional step. All right, so, in this particular problem, we're going to have a 2 liters of mixture, 2.00 liters of mixture, and it's going to be oxygen and helium. And the total pressure is 658 torr. And so the 2 ways of visualizing it, well, one way is by Dalton's. In Dalton's, I'm going to have 2.00 liters of oxygen, but the pressure is going to be 270 torr, plus I'm going to have 2.00 liters of helium, and the pressure is going to be 388 torr, 388 torr helium. That's one way of visualizing. That's the way we did this one, is because we took the pressure of oxygen plus the pressure of helium to get the total pressure, 2 liters of each. The other way of visualizing this is by Avogadro's. If I visualize this mixture as Avogadro's, how much oxygen do I have? Well, how much oxygen I have, one number I can come up with quite quickly. And that number is, I have how much oxygen? I have 658 torrs worth of oxygen. But what's the volume? 0.82. The volume of oxygen would just take the pressure fraction, that is 270 out of a total of 658, times the volume, 2.00 liters. So we take the pressure. It's because the percentage by pressure is the same as the percentage by volume, which is the same as the percentage by mole. And what did you get here? 0.820. And so I'm only going to have 0.82. 0 liters. All right, plus how much helium do I have?
1.18.
Well, I'm going to have 658 torr worth of helium. The volume would be 1.18.
Yeah.
0 liters. Oxygen, helium. So these are the 2 ways we think about this particular gas mixture after we do the expansion of the volume, increase the volume. Number 5, a sample of wet hydrogen was collected over water. Let's take a look at that figure. This is the figure here. So the hydrogen is being generated in this reaction. It's going up here. And then it's being bubbled up here and collected in this jar. What happens is this: when hydrogen is bubbled through water, it becomes wet. Not literally wet, it becomes wet with humidity. And so it's like, people have these humidifiers, they bubble air through the water. They bubble the air through the water, the air becomes a lot more humid. And so whenever we bubble a gas through water, it becomes saturated with water vapor. It becomes quite humid. And so let's take a look at this next problem here. A sample of wet hydrogen was collected over water. All right, so what happens is we start off with dry hydrogen, or just pure hydrogen gas. And that hydrogen gas is bubbled through water. And what happens is that hydrogen gas gets saturated with water vapor. So the hydrogen gas comes up here, we have the hydrogen gas collecting up here. But also collecting up there is gaseous water molecule, like this. And so we end up with this. We end up with something called wet hydrogen. Wet hydrogen is a mixture of hydrogen and what? And water vapor. So wet hydrogen is a mix of H2 gas and H2O gas. Okay, so let's take a look at our wet hydrogen, which is hydrogen and H2O gas. And this mixture is going to be at 19 degrees C. And the pressure of the mixture is 733 millimeters of Hg. And they tell us that the pressure of the water vapor, that is the pressure of the gaseous water, is 16.5 millimeters of Hg. So what is the pressure of the dry hydrogen? And so we have the total pressure. The total pressure is going to be the pressure of the hydrogen plus the pressure of the water vapor. And so we could calculate the pressure of the hydrogen. The pressure of the hydrogen is just equal to the total, P total, minus P water vapor. The water vapor they gave us, the water vapor is 16.5 millimeters of mercury. And so we can figure out the pressure of the hydrogen. So again, this is the Daltons. In fact, they don't do any Avogadros in this, I think. Let's do it here. 733 minus 16.5. 716.5. So the pressure of the hydrogen is 716.5 millimeters of mercury. Subtract the 2. So let's see what they did. Did the total pressure minus the pressure of the water. Sodium metal reacts with water to produce hydrogen gas according to the equation. In an experiment, the hydrogen gas is collected over water in a vessel where the total pressure is 745 torr and the temperature is 20 degrees C, at which the temperature of the vapor pressure of water is 17.5 torr. Under these conditions, what is the partial pressure of hydrogen? If the wet hydrogen gas formed occupies a volume of 8.04 liters, what number of moles of hydrogen is formed? Okay, so the pressure is 745 torr for this mixture. temperature is 20 degrees C, and they tell us, this is the total pressure. They tell us that the pressure of the water vapor that results. The pressure of the water vapor is 17.5 torr. Now, the pressure of the water vapor is interesting because the pressure of the water vapor only depends on the temperature. So what happens is this, you put some water into a container and the water starts to evaporate. But eventually you'll hit a point where you get something called 100% relative humidity. When we're at 100% relative humidity, no more water evaporates. Actually, that's wrong. Water continues to evaporate, but no more net water evaporates. What I mean by net water is this. We have evaporation, but we have an opposing process. The opposing process is called condensation. And so water never stops evaporating. Water continues to evaporate, but as we get more and more water molecules in the gaseous state, more and more water molecules condense. And so that's what this reverse arrow is. Eventually we're going to hit the point where the evaporation rate is equal to the condensation rate. So for every 10 water molecules that evaporate, 10 water molecules condense. And so there's no more net change. Once we hit that point, it's called 100% humidity. What we do is we can measure it. At 100% humidity, it doesn't matter the size of the container. If I cut the container in half, I'm going to have the same pressure. I won't have the same volume. And so the best thing to do with this is to do it via Dalton's, where we look at the pressure. Now, the amount of water that vaporizes is a function of the temperature. And so if we look at this, we can determine this by taking measurements and then compiling that data into a table. And so if we look at vapor pressure of water, we get a table like this, or we can graph it. It's ice, sorry. Pressure of water, ice. Get a table like this. This is 100% relative humidity. So if I hit this pressure for water vapor, then that's it. I can't get any higher than this. A lower vapor pressure than this means more water evaporate. But once I hit this, then it's saturated. And so at room temperature, which is 25 degrees C, at room temperature, 100% relative humidity corresponds to having enough water in the gaseous state to generate 23.8 millimeters of mercury pressure. So this is the vapor pressure when it's saturated. As the temperature goes up, the humidity can go up. It's still 100% relative humidity, but the humidity will be much greater because at 70 degrees C, the vapor pressure can go up to 233.7. Still 100% relative humidity because it's saturated, but the percentage water vapor in the gaseous phase has gone up dramatically. Okay. 17.5 torr. Under these conditions, what is the partial pressure of hydrogen? Okay, so let's go ahead and try to visualize this mixture here. This mixture is going to be some volume, 8.04 liters. this is going to be wet hydrogen. Wet hydrogen is hydrogen and water. H2 and H2O gas, water vapor. The total pressure is 745 torr. So the pressure of this mixture is 745 torr. And the total pressure is equal to the pressure of the hydrogen plus the pressure of the water vapor. And so the pressure of the water vapor is given. We get it out of a table, 17.5 torr. That's it. And so it's been saturated as a 100% relative humidity. And then we solve for the pressure of the hydrogen. The pressure of the hydrogen is just 745 minus 17.5. 745 minus 18. 727 torr. Should be it. Does that look right? Okay, now what we're going to do is the next thing. They want us to calculate the moles of hydrogen that are formed. And so the moles of hydrogen are going to equal the pressure of the hydrogen times the volume of the hydrogen over RT, the temperature of the hydrogen. So it's important that we get the right pressure and the right volume. So in this case, if I want the moles of hydrogen, what is the pressure of hydrogen? 745 torr, okay. So if I say the pressure of the hydrogen is 745 torr, then what is the volume? 8.04 liters. Okay, now, which way are you looking at the gas? Are you looking at it by Dalton's or are you looking at it by Avogadro's? Because these are not mutually consistent. It's either one or the other. You could have it 745 torr, no problem. You could say it's 745 torr. That's looking at it by Avogadro's. Or we could say it's 8.04 liters. That's fine, but it can't be both simultaneously. If we say the hydrogen is 745 torr, then the volume is going to be a fraction of the total. If we say the pressure is 727 torr, then the pressure is a fraction of the total. The volume is going to be the total, be 8.04 liters. And so what it means is, this is what it means. It means that if we have 8.04 liters of hydrogen, that means we're going to have a percentage or a fraction of the pressure. So if we say it's 8.04 liters of hydrogen, then that fraction of pressure is going to be 727 torr. Or if we say that we have, this is, if we say we have 745 torr of hydrogen, then the volume is going to be a fraction. And so what is the fraction? Well, what was the fraction for the pressure? If we look at the pressure fraction is going to be 727 out of a total of 745 times 100%. And so we have to do one or the other. And so the volume fraction over here is just gonna be this. It's gonna be 727 over 745 times the total volume. The total volume is 8.04 liters, which is gonna give me 727 divided by 745 times 8.04 gives me 7.8545. 7.845 liters. So I have a choice. I could use this volume of hydrogen, but if I use this volume of hydrogen, I would have to use this pressure of hydrogen. Or I could use this pressure of hydrogen, but I would have to use this volume of hydrogen, which is a fraction. I could do one or the other, but I cannot do both. This is why when we think about mixtures of gases, we're either going to orient ourselves in Avogadros or we're going to orient ourselves in Daltons. We got to pick one or the other. We can't do both. It doesn't matter which one you pick because they're both going to give us the same answer, you know? Because it's just pressure times volume. Pressure times volume. When I do pressure times volume here, I'll get the exact same numbers doing pressure times volume here. And so we just pick one and then try. So, the easiest in this case is just to leave it in terms of Daltons because they tell us the pressure of the hydrogen. We have the volume of the hydrogen and the pressure of the hydrogen. So we can just do it that way. Here. This gas mixture stuff is not easy, you know. People get this all mixed up all the time, and so it takes some time to figure it out. And so just to be aware of that, it's challenging stuff, but once it clicks, then it should be pretty straightforward. All right, we'll